Now for probably the most critical part of the lesson. This is the technology section, so pull out that calculator and get ready to go. This time I'm giving you f prime of x. I'm defining that, and that's going to be defined on the interval 1 to 4, open interval. Make sure, please, that your calculator is in radians. If you're coming from science class, turn it off of degrees, put it on radians. Okay. Here's the first thing we need to do. We're going to go into our calculator and we're going to define y1 to be this derivative equation. So it's going to be x to the power of 3. But something very important that you're going to want to remember for your AP test and for my test, that when a function is written as polynomial times trigonometric, for some reason some calculators do not recognize that as multiplication. So we need to insert a multiplication symbol. That's a little star. If you type times on your calculator, it's going to give you this little star. So x to the power of 3 times the cosine of 2x plus 1. So type that into your calculator. The next thing you're going to want to do is change your window settings to be x min 1, x max 4. And then your y could be -5 to 5, -10 to 10, something along those lines. Okay, make sure you have this all in your calculator. Now let us graph this derivative function. Ordinarily, you do not have to show the graph. It's just like the no point number line. You don't have to show it. In fact, I wouldn't show it, but for your notes, I totally would, so that you can refer to it later. So here's our window, and it's going to start with 1, 2, 3, and then 4. When you graph your derivative, it should look something along the lines of this. Perhaps you need to narrow it in so that you can see that curvature. We're going to call this function y equals f prime of x. That's very important. This is a derivative function. You will notice that here, when it's above, f prime of x is greater than 0, and when it's below, f prime of x is less than 0. So I imagine you know what to do next. You're going to find these zeros. In finding these zeros, you are finding the critical points. So make sure on your paper, if you get critical points, you say where they're coming from. So I'm going to say that f prime of x equals 0 at, then I find these critical values. Make sure you're doing that, practicing it, and we get x equals 1.856 and also 3.427. Those are our critical points. Part A and B are repeats of lesson 1, so let's take a look. Part A, where is f decreasing? F is decreasing on some interval, and the reason for that is going to be because, do you remember, f prime of x is less than 0. So I have to literally see where this graph function is below the axis. So we will say that f is decreasing on, I'm going to use 1 in parentheses because it's not in the domain, all the way up to 1.856. I use bracket for standardization, and union with 3.427 all the way up to 4, which is also not in the domain. And that's because f prime of x is less than 0 on the open interval, as shown here. Now in part B, it wants to know where we have a local maximum. So remember, you have to go purely on theory. You can't look at this graph. This here is not a maximum. That's the maximum of f prime, but we want the maximum of f of x. And you remember that occurs where the derivative changes from positive to negative. See here, the derivative is above the axis. Here the derivative function is below the axis. So the point that I just circled represents where the function will have a relative max. So we will say now that f has a relative max at x equals the 3.427 because f prime of x goes from positive to negative at x equals 3.427. It is really important to note that you needed to write this on your page somewhere. If you did not write that on your page, then they would not allow B to be the full justification. It is correct to say that f prime went from positive to negative, but we needed this information on our page together with the changing of derivative sign in order to make that claim. If we don't say this somewhere on our paper, then we will lose credit for the justification of relative max or relative min. Now in part C, it wants to know where the graph of f is concave down. The theory behind concave down is where the second derivative is less than 0. So we are going to take a moment to graph the second derivative function. This is the same window screen. 1, 2, 3, 4, and 1 is over here. To review that, we have from our home screen, we're going to take the derivative of y1 of x with respect to x. We're going to highlight the answer, and then we're going to copy the answer. We'll go to y2, and we will paste the answer. And then we're going to graph y2, which will represent the second derivative function, f double prime of x. So I'll come over here and draw this. Mine went off the page a little bit, and it came back down like that. Okay, this we're going to label as y equals f double prime of x. When it is above the x-axis, f double prime of x is greater than 0. Below, f double prime of x is less than 0. I'm going to use my calculator to determine where f double prime of x equals 0, and that occurs at x equals 1.469, also at 2.882. Okay, and so we are going to determine where the function f is concave down. That's going to occur when the second derivative is less than 0, or in other words, when the second derivative graph is below the x-axis. So let's write our answer for part C. And that's going to be f is concave down on the open 1 to 1.469 in union with 2.882 to 4, because f double prime of x is less than 0 on this interval. In summary, you do not have to draw the graphs on your paper, but you certainly have to produce the graph on the calculator so that you can look at it, find the zeros, and then make your connection with the theories of concavity, point of inflection, increasing, so on and so forth.